Hi everyone. It is my honor to be on this online platform of Computer Graphics International 2020. I will present our work, Feel the Insight, a haptic interface for navigating stress distribution inside objects. This is a collaboration work by Lifeng, Rubin, Dapeng Chen, Aiguo, Ning, and Yin Yang. We are from Southeast University, Nanjing University of Information Science and Technology, Nanjing Forestry University, and Clemson University. I am the presenter, Lifeng. First, let me talk about the motivation of our work. Stress distribution reveals how forms interact with varying load configurations. It is essential to preview the stress in a design process. It can be used to predict the material fatigue or material failure. The early assessment of the stress field in use is helpful to accelerate the design iteration. At the special physical quantity, stress tensor expresses the internal force that neighboring particles of a continuous material exert on each other. It is a three-dimensional tensor field in nature. First, each point inside an object associates with a 3D tensor, which can be encoded as a 3 by 3 matrix. It is not straightforward to map the tensor to visible data. Second, the tensor field inside an object is 3D volumetric data. To display the 3D distribution of tensors inside a volume is also challenging if we do not hope the structure inside will be occluded. Traditional methods to display the tensor field rely on glyph-based method, which maps the 3D tensors to primitives such as frames, ellipses, or boxes, and then draw the primitives on the screen. Another way is to use streamline-based method or texture-based visualization, which still require volume rendering techniques to map volumetric data onto the screen. Therefore, a typical way to deal with the 3D volumetric data is to cut the 3D model into 2D slices and only show the data distribution on 2D slices. However, it is not effective to frequently specify the cutting planes and switching between different slices to perceive the 3D data. What's more, in general product design, the engineers may need to check the stress distribution under different or time-varying load configurations. Take this into consideration, the interaction with the stress distribution gets even more complicated, making the traditional method not effective. In this work, we propose a haptic user interface for navigating stress distribution inside objects. This short demo overviews our solution. The user is allowed to interactively edit the load configuration with the left hand and perceive the stress distribution inside the model by probing his right hand into the 3D model. These two interactions can be tightly combined together to support navigating stress distribution inside a 3D model under varying load configurations. First, Let us look into the interaction of the left hand. A user first locates his hand into the 3D model and registers it at the rest pose. After the registration, the user is allowed to change the hand pose. We check the displacements of the finger joints inside the model and map them to the loads. Then, we use finite element method to simulate the stress distribution under the loads. As the left hand moving, we obtain the corresponding time-varying stress field. To perceive the stress field, we design the interaction to use the right hand. As shown in this figure, we use a hand tracking sensor to obtain the pose of the right hand. We use leap motion in our work. Then, the stress is mapped to forces and applied on the moving fingertips by using a wearable haptic device. Let us look into the wearable haptic device here. This is the wearable device which we designed for the haptic interface. It moves a tactile on the fingertip and produces skin stretch. The device is composed of 4 parts: a static platform with an adhesive connector, a modal module, a slider, and a spherical tactile. The motor rotates to drive the slider moving along the finger direction, and the connected tactile produces skin stretch at the fingertip. We 3D printed our design, and the wearable device had a lightweight and a small size. And the moving range of the slider is within 9 millimeters. The refreshing rate is about 30 milliseconds per frame. To better understand the perceptual resolution of the introduced device, we run a just noticeable difference test, a JND test. In this test, we employed 12 participants and use a simple up-down method to evaluate the differential threshold. The reported Weber's fraction is about 0.092. With this observation, the perceptual resolution is estimated to be around 30 levels. In a nutshell, a user is able to perceive 30 levels of forces with the proposed device. With the design hardware, we are ready to map the stress to the force applied on the fingertip. Note that the stress tensor actually encodes how the force varying along different directions. We therefore record the moving direction of the fingertip Ni. By computing the position of the fingertip Qi and its position in the last frame Qi'. Then we look up the tetrahedral L, where the fingertip Qi locates in, and find the corresponding stress tensor SL. At last, we compute the directional stress SI of SL along the direction Ni, and map the directional stress to the force and display it using the wearable haptic device. This is the overall diagram, illustrates our interaction design. By introducing a bimanual interaction with a haptic interface, we allow to support varying loads and perceiving stress in one session. We then evaluate our design. First, we test the single finger interaction with our method. In this test, we employ 12 participants to perceive the stress distribution inside a box region. As shown in this figure, along the line inside the box from the left to the right. We test a glyph-based visualization using VTK, the visualization toolkit, with and without the proposed haptic interface. We randomly display stress fields to the users. The participant is asked to answer the stress distribution, what they have perceived. For example, they will specify if the stress is increasing or decreasing, or first increasing then decreasing, along the center line. We collect their answers and find the ratio of the correct answers at the accuracy. As shown in the lower left subfigure, with the haptic feedback, the accuracy is significantly higher than using the glyph-based visualization. After the test, we also asked the participants to rate their overall preference. The results also indicate that the user shows their preference with haptic feedback. We then evaluate our interface with applications in engineering design. We prepare an architecture design as shown in the right figure. In this test, we employ 7 participants with engineering background. After a 10-minute long introduction of our system and a 3-minute long free exploration of our system, they are asked to complete the following tasks. First, they are involved in a by-finger test. In this test, a user wears 2 haptic devices on the index and middle fingers. Then, they move the right hand in the stress field and are asked to compare the forces applied on 2 fingers. The 3 cases that the force on the index finger is larger, the force on the middle finger is larger, and the forces on the 2 fingers are similar, are to be reported. We check the ground truth and find whether the reported comparison is correct, and regard the ratio of correct answers as the accuracy. We plot the accuracy with respect to the difference of the slider movement, as shown in this figure. The overall accuracy is about 86.5%, and the accuracy gets higher if the difference of forces on the 2 fingers is greater. At last, the user is asked to find the weak region of the design. In terms of the weak region, we mean the regions with the largest stress under different load configurations. We randomly sample the loads on the architecture model. If a vertex on the model was chosen as the weakest vertex for a large amount of times, we regarded it as a weak vertex. We group neighboring weak vertices to form weak regions and highlight 9 weakest regions of the model in this figure. Then, the user is asked to find a weak region of the design by using our user interface. For all the participants, it takes around 3 minutes to complete the task. In comparison, it takes hours to varying load and check the volumetric data using traditional graphical user interface. We also interview the participants and collect their feedback. Generally, they find our system convenient, intuitive, and fun. They also provide suggestions, such as they hope we could filter the noises. They expect a personalized design of the haptic device or to reduce the weight of the device for long-term interactions. Please check our paper for more details. In summary, We propose a haptic interface for stress distribution inside a 3D model. We design our interface to display stress tensor using a haptic device to show the varying force along moving trajectory. We use a 3D user interface to allow users directly probe into the 3D volume, and use a bimanual interaction to allow varying load, configuration, and displaying the stress in one session. In the future, we will work for a miniature hardware design with both force and torque feedback, and extend our interface for more applications. We will also study how to leverage the information from visual and haptic channels to further improve the efficiency in understanding stress fields, and try to display more topological properties of the field and more material properties of the model. Thank you for your attention. I am now free to take any questions. Thank you.